It's David Spears, Civil Engineering Instructor at Texas Tech University, talking about solid CE 3302. We're in Chapter 12. I've kind of adapted this example from a problem P12-1F in the book. I've added a load to make it a little bit more complex. What you're supposed to do is to develop an equation for the elastic curve of this beam under this loading condition. 4 meters long, mid-span load of 5 kilonewtons, uniformly distributed load over the right half, 3 kilonewtons per meter. Designated the points on the left and right as A and C. First thing to do is, and I'm going to say X runs from the left side for both of my equations. So first I solve for my reactions by taking the moments about C, and I solve for AY's to be equal to 4 kilonewtons up. Sum of forces gives me CY is equal to 7 kilonewtons up. Okay, now for these equations and solving these elastic curve by integration, I have to write an equation for the moment on every segment that has a different loading condition. So fortunately I only need 2 equations, one in this first segment here between the support and where the loads start occurring. That's what I call segment 1. The second one will occur over here in this area where the loads are. We'll deal with that in a second here. Segment 1, draw a little free body diagram, show the loads, which is all I have is the reaction, 4 kilonewtons up. Then I have my what I call my X1 distance, because it's the first one for segment 1. I have a shear in a moment at that section, and I don't care about my shear right now. So I should write an equation for my moment by doing sum of moments about that point where I've cut my section. Sum of moments is 0, counterclockwise is positive. All I have is negative 4 times the X1 distance, negative because it's clockwise, plus M. So obviously the equation for the moment in that segment X1 is 4 times X1. And that's going to be in the units of kilonewton meters. So what I need to do to get a slope equation, which I'm going to call theta of X, is integrate it once. Don't forget that I have this EI constant in this equation, and I'm just going to kind of show it once and assume that you know it's in there for all these equations. I have to integrate 4x dx from 0 to 2. So I do one integration of that to get my slope equation, which is 4x squared over 2, plus a constant of integration C1. And I integrate it again, integrate this equation again to get the deflection, which I'm going to call delta for this example. Delta of x at location x is the integral of this equation, which is really 2x squared plus C1. Integrate that once, and I get 2/3 x cubed, that's x1 cubed, plus C1, my constant of integration, times x, plus another constant of integration, C2. Now I move on to segment 2, which is between the midspan where the loads are occurring and the end. Here's my little free body, kind of all jumbled together. The forces acting on it are my 4 kilonewton reaction here on the left, my 5 kilonewton load in the midspan or at 2 meters out from the left end, my uniformly distributed load, which I have kind of shown the resultant of. At any point X out here between B and C, the distance that the uniformly distributed load is acting on is X2 minus 2 meters. And so the uniformly distributed load resultant is 3 times the quantity X2 minus 1 kilonewtons. It, of course, will be acting, we'll talk about the distance here in a second, So I do a sum of moments about that section, and counterclockwise is positive. Sum of moments at that point is 0. It's negative 4x2 for the moment caused by this 4 kilonewton force. About that point, 4 times x2. It's negative because it's clockwise. Plus 5, my midspan load, 5 kilonewtons, times that distance that I just talked about there. x2 minus 2 is that distance right there. That's the moment arm of the 5 kilonewton force. It's counterclockwise, so it's positive. Plus my uniformly distributed load, the moment that creates, is 3 times x2 minus 2 for the quantity, the resultant force, times its moment arm, which is half of that distance, x2 minus 2. So I have to just kind of be clever and write out these equations and think about the math and the geometries involved. And finally, I have the force, the moment in each section in that x2 span, segment 2. It's also positive because it's counterclockwise. Now I just kind of do the math and combine all my common terms. I get negative 4x2 plus 5x2 minus 10 for this expression, plus 3 halves. I'm just taking this 2 over here and dividing it into the 3. 3 halves x squared, and doing the math of x2 minus 2 quantity squared. And I come up with this expression, these 3 terms. Negative 3 halves times 4x2. Or first, negative 3 halves times x squared minus 3 halves times 4x2, the combination of these second terms. And then 3 halves of 4, which is just 2 times 2, plus m2 is equal to, combining all the common terms, 3 halves x squared minus 5x minus 4 plus mz. So I can rearrange, and I can say that the moment at any segment, any section cut, there is negative 1.5x squared plus 5x plus 4. Therefore, I want to integrate that once, which I haven't shown as nicely as I did up here, but I integrate it once to get EI theta of x is negative 1.5 over 3x cubed plus 5 halves x squared plus 4x2 plus another constant of integration, C3. Integrate that again to get my deflection in that section, and I get this number, this expression, negative 0.5 over 4x to the 4th plus 2.5 over 3x cubed plus 4 halves x squared plus C3 times x plus another constant of integration, C4. Can rearrange all that, or simplify it all down to this expression right here. So that's my elastic curve expression over the second half, or the segment there. So I put boxes around my 2 slope equations, 1 and 2, and my 2 deflection equations there and there. Now I've got 4 equations, 4 unknowns. So here's why I have to go to boundary conditions to get solutions for those constant of integrations. I have 2 boundary conditions that are basically at either end, x equals 0 and x equals 4 at the C end. My deflection delta is equal to 0. The first one's nice and easy. If I plug in to this equation right here, my first segment deflection equation, or elastic curve deflection equation, I put in 0 for both these 2 values of x, and I get that C2 is equal to 0. My other boundary condition is not as easy. I just have to plug into the section 2 value of x 4 meters, because at that support the deflection is 0. So I just plug that into this, plug 4 into x in this equation, and I get this expression. I can do the math, combine the common terms, and I can come up with C4 is equal to this expression of C3, negative 4C3 minus 53.3. Okay, now I still have two unknowns. I have two continuity conditions that I can use. And they are that at x equals 2, right here in the middle where my two equations come together, at x1 is equal to x2, which are both 2 meters, the slope is the same. So those two expressions have got to be equal to. So I plug 2 into this equation and this equation, and I get this. That's equal to, the slope is, I don't know what it is, but I know it's going to be equal. So it's 2 times 2 squared plus C1 is that equation with 2 for x. This equation with 2 for x looks like this, plus C3. So I get some expression plus C1, some quantity plus C3. I can simplify that all out and rearrange it, and I get that C1 is equal to C3 plus 6. So the other continuity condition I have is that the deflection at that point x equals 2 is the same from either equation. Kind of obliterated some of my number there. Okay, so now I just want to take these two equations for deflection, or my elastic curve equations, and substitute in x equals 2 into those two and set them equal to each other, this one and this one. That looks like this. 2/3 x cubed is this one. No, this one right here. It's confusing. With 2 is x, plus C1 times 2 is equal to this expression. With 2 in there is x. I can do all the math, combine the common terms in this math. Pause the video if you need to look at that closer. I finally end up that, then I get it down to this form, and I can plug in C4 is equal to negative 4C3 minus 53.3, and C1 right here is equal to, where did I solve for that? Right here, C1 is equal to C3 plus 6, so I can plug all that into this big long equation, combine all the terms, and I can get down to 4C3 is equal to negative 58. So C3 is equal to negative 14.5. Then I go back into those two equations, and I can solve for C4 and C1. Ran out of room, but so my elastic curve would look, I'd have two equations for them. And one would be this expression with C1 and C2. C2 is 0, C1 is this value down here. This expression for the segment 2 with C3 and C4 is evaluated right here. So the key is writing a moment equation based on the segments. I have to have two of them because I have really two different, or I have a change in loading that occurs right there in the middle. And then using these boundary conditions of the deflection at the ends, in this case were equal to 0, and the slope and the deflection in the middle where the two equations come together is equal.